go through our formulas from yesterday, and I also want to go through a handful of questions that are similar to what you'll see in 5-1 Day 2, which that date has expired, but it's getting pushed back, so don't worry about it. And if I need to put more examples on there, or more similar exercises, I can do that for you if you're a person that didn't hear me say yesterday that was not due today. But linear velocity, okay? The formula for linear velocity, or you're going to see from time to time they call it linear speed, and we'll talk about the difference in those two things later. It's really not a big issue right now. But linear velocity, we said yesterday, comes from the fact that distance is equal to rate times time. And then if we divide both sides by t, we get rate is equal to distance divided by time, right? Okay, and if you think about it, when you're traveling in your car, and it says I'm going 60 miles per hour, your 60 is your distance, and your 1 hour is your time, right? So 60 miles per hour is a rate, okay? And then generally speaking, rates are things that unit-wise cannot be converted from one to another. So miles can never be converted to hours, and hours can never be converted to miles, right? So it's left as what we refer to as a rate. You can have the same thing in regards to like hourly pay. Okay, you call it an hourly rate. It's the dollars you make per hour. Okay, or maybe the dollars you make per week, or something like that. You can't change money into time, and time into money, right? You got miles per gallon. Can I change a distance into a volume, or a volume into a distance? It's impossible to do. So we leave them as rates. So that's what we're talking about when we see the word rate at any time, is that your units essentially are not going to be able to cancel each other out. Okay. When we look at linear velocity, we could use that formula, but it's maybe not as obvious or specific as it needs to be when we're talking about the idea of having our circle, okay, and we have an object on that circle, and that object on that circle is traveling around the circle at its particular speed, okay. We want to know, how does that speed kind of transfer to that object kind of moving along a straight line, okay. And I don't know if I showed you this one yesterday. I don't think I did. If I've got, and we'll see an example like this where we need this visual as well. But I've got a tire here. I've got my road. If I spin my tire, you see that the circumference is laid out on the road, right? So after one complete revolution of my tire or my wheel has traveled the circumference of that circle, right? Does that make sense? Okay. Well, if I'm able to, maybe rotate this, and let's say it takes me 5 seconds to do that. Okay. So we could take, if that took me 5 seconds to unravel that wheel, essentially, to go through one revolution, I now have this linear distance, which is equivalent to the circumference, right? And if I divide that by a time, would it have told me how fast that wheel was moving? Does that kind of make sense? Okay. And the idea is, if no matter where, if I put a point, let's see if I can do this. If I put that point G on that wheel, as that wheel is moving, point G is moving, right? Point G has a particular speed to it, okay? Linear velocity is going to describe what that speed is for us, okay? So that's what we talked about yesterday. But now, redefining some of these variables, okay? We could, like I said, we could use rate is equal to distance divided by time. But when we have R here and we're talking about circles, a lot of times there might be confusion that R means radius, right? So instead of R for our linear velocity, they use V, or we've decided to use V, Okay. Now distance traveled, because we're dealing with a circular path, the distance traveled is circumference, right? Does that make sense? Now I'm not going to write 2 pi r, because what if I don't travel the entire circumference? Or what if I travel multiple circumferences? Okay. What if my wheel goes through multiple revolutions or rotations? The distance traveled around a circle, no matter what portion or what multiple of that circle you travel around, is an arc length, right? And we talked the other day that an arc length we denote as S. And I'll talk about maybe a different way to write that here in a minute. And then our time is going to be a consistent T. It's going to be a time. Okay? But we also know from what we talked about 2 days ago, I believe, that arc length, S, is equal to r theta, right? Okay, where theta is in radians. So we have the ability to write our linear velocity as either S divided by T, or if we go r theta divided by T. Is that okay with everyone? Okay. Now the next thing that I think is important to talk about is angular velocity. And remember yesterday we kind of mentioned that angular velocity, if that angle right there is theta, we're interested in how fast is that theta changing. Okay? Well, in order to figure out how fast something changes, we need to know how big that thing is, and we need to know the time that it took to get that big, right? That kind of makes sense? Okay? Essentially it's the same thing as what we just talked about with this idea. If I want to find out linear velocity, that's a distance divided by a time, right? That's how fast length is changing, essentially finding, how fast did this segment change? How fast did this segment grow in regards to a time? Okay? So in regards to angular velocity, we're looking, that's not a circle anymore, or at least not centered, there you go. We're looking at how big that how fast that central angle is changing. Okay? So the central angle is always theta, and we're going to divide by the time that it is changing in regards to. Okay, so we use the variable omega here. It's a weird looking W. Okay, and we say that omega, or our angular velocity, is equal to theta divided by time. And again, we're going to have theta. If it's not specified, theta is in radians. Okay, so this is our angular velocity or angular speed. Okay, so those are two formulas that are pretty useful to us, but there's a link between them. Okay, and if you look at them variable-wise, hopefully you can see the link that linear velocity has theta in it, right? That's the exact same theta. Linear velocity has time in it. That's the exact same time. Okay? So what we can do, and there's several, like I said yesterday, there's several different ways you could do this to essentially get the relationship that we want. If I take linear velocity is equal to r theta divided by time, and I take omega is equal to theta divided by time, I'm going to solve this one for theta. Okay? Or, you can solve this one for theta as well. Let's actually, I think maybe it's a little bit quicker to solve this one for theta. Let's solve that one for theta. What would I need to multiply both sides to solve that one for theta? Okay, so I get omega t is equal to theta, right? Well, let's take that theta now and put it in right there. Okay, so I now have v, or linear velocity, is equal to r, but theta is now omega t, right? Does that make sense to everybody? Divide that by t, because of that time right there. What happens to your t's here? Cancel out. Linear velocity is equal to your radius times your angular velocity, or omega. Is that all right? I think yesterday we did it this way. We said V is equal to r theta over t, and then I had what omega is equal to theta over t. I went Vt over r is equal to omega. Plug that, or sorry, no, theta, sorry. Plug that in here for theta, and you get omega is equal to Vt over r divided by t over 1. It's going to get the same result, but the algebra is a little bit more complex here. Multiply by the reciprocal of 1 over t, and now your t's cancel, right? That t and that t will cancel. So it leaves me omega is equal to v divided by r, which is perfectly fine. Omega is equivalent to your linear velocity divided by your radius. But like I said yesterday, a lot of your textbooks will not write it that way because of the ratio. It's like, when we first introduced distance equals rate times time in 7th or 8th grade, we write it that way, and then we let you come up with the different, solve for R, solve for T type thing, right? So here, a lot of times they're not going to write this formula as a ratio. They're going to multiply both sides by R. I get R omega is equal to V. Is that the same thing as that? Okay. So that's something to think about, several different ways to get that. But what that does is now you see if there's a linkage between, or there's a relationship between linear velocity and omega, right? Your linear velocity is your omega, or your angular velocity, times the radius. And that's maybe a useful fact at some point throughout some of our questions. Now, if I look at all of these things, and I'm going to delete these and just write up here that that linear velocity is equal to r times omega, something to think about. But a lot of these have theta in them, right? And even when I do this, omega has theta wrapped up inside it, okay? So we need to know what theta is. And theta is always going to be 2 pi, okay, times the number of revolutions that you pass through, whether it be the angle that we're interested in, or there's a, you can talk in terms of angular velocity or linear velocity, either one of those ideas or concepts that we're dealing with, we're going to need to know theta, and it's that number of times that essentially that you are moving around your circle. Okay. Now revolutions, a lot of times revolutions is going to be a multiple number. So like think about like in a car, if you're in your car, look at your dashboard, and usually next to the right, like next to the speedometer or something like that, it should say RPMs, and your dial just goes like 1, 2, 3, 4, 5. Okay. But if you look at it, it says RPMs, and it says like 1 equals like 1,000 or 10,000 or something like that. So when you're tacked on your RPM dial goes to 2, you're actually going 20,000 RPMs. Does that make sense? Okay. So that's what we're kind of talking about here is when they talk about revolutions, it's how many times you are traversing around this circle. Okay. And like I said, a lot of times it's a multiple number, okay? But it doesn't have to be. It could be half a revolution. It could be a third of a revolution. It could be any portion or multiple of a revolution. Is that all right? Okay. We're going to do a question at some point where we're dealing with the Earth, and maybe we're running around the equator or running around a meridian, okay? And I don't get around the whole thing. I only get around maybe a third of it. And I want to know how fast were you traveling, okay? So we could have 2 pi times a third, and that would tell me that angle that I'm dealing with for that theory. Does that make sense? Okay. So those are some formulas that I think are very important for you to understand. I'm not saying you have to memorize them. My hopes are that you realize that they just basically come from the distance equals rate times time formula, and then there's several relationships there. I think what you're going to find out in this trig class is that we spend some time doing the algebra, the analytical algebra, to analyze formulas, understand formulas, so that you can use that skill maybe later on in a more advanced class, like a calculus class or something like that, or a physics class, and you see a formula and you want to investigate that and pick it apart and understand it a little bit better. Hopefully build some of those skills to do that here. But on your, I believe you're going to get a reference sheet for this course as well, kind of like the one we got last course. There's going to be a lot of formulas on that reference sheet. I'm assuming that these 4 will be on there. When I give you a quiz or a test over this chapter, I will give you those 4 formulas. My main concern right now is, can we apply them? Can we use them inside a problem? Not necessarily be the formula that keeps us from answering a question. Is that all right with everybody? All right, so let's do some examples with these. And these are similar to what you're going to see on WebAssign. Okay, so I just picked them out of that 5-1 day 2 assignment. Here it says a car's wheels are 36 inches in diameter. Okay, 36 inches in diameter. That's something to pay attention to as well. Just a detail that they like to flip back and forth between diameter and radius. So make sure you do that. Okay. It says, how far in miles will the car travel if its wheels revolve 10,000 times without slipping? The idea is that when you are driving, okay, there's a friction coefficient. You guys talk about that in physics at all? Okay. There's slippage when you're driving. Okay. We want to negate that. We want to make sure that we're not talking about that. Okay. Because if there is slippage, then my wheel is turning, but I'm not gaining any horizontal distance. So that makes sense? Okay. So we're going to negate that. There's a lot of things in maybe a physics class that you guys deal with friction that you either negate it or try to deal with it, and you see that when you do try to deal with friction and try to incorporate it, it often makes things very cumbersome. Okay, so a lot of times as mathematicians, we like to just say we're not going to deal with it. Don't worry about it. The idea here, if we've got this car wheel moving, it's this concept right here. Okay, my radius is, whatever wants to be 18 inches, so maybe that's 18 inches there. If I spin my tire one time, if I get in my car and I let it start rolling and I stop after my tires have made one complete revolution, the distance my car has traveled would be equivalent to the circumference of the wheel of my car. Does that make sense? Okay. So what we're going to do is we're going to do that in this problem 10,000 times. So we're taking this distance here, which is equivalent to the circumference. But we're taking that distance now as a linear distance, and we're going to kind of use the segment addition postulate and put 10,000 of those segments end to end with one another. All right, and then talk about, okay, if we've done that, if we've got that distance, how far is that? Okay. So what are we talking about here? When we talk about the distance that we are traveling, we're talking about arc length in this case, aren't we? Or thinking about back to geometry, we did it this way. We use this formula, which might be something that maybe is a little bit more informative. If we were in degrees, we've got 360 there. That would be the formula we talk about in regards to arc length. Well, if theta is 360, if theta is equivalent to one complete revolution or one complete cycle of my tire, then we know that fraction becomes 1, right? We have 1 times circumference. So we traveled 1 circumference of our circle. Well, if we go 2 revolutions, that becomes 720. 720 divided by 360 is 2. So now we have 2 circumference. So 2 times 2 pi r. Does that make sense? Okay. Well, we're not dealing with degrees. This is everything that we're doing here with these arc lengths is in radians. So if I go and say I do 2 pi, I could do the exact same thing. So 2 pi, 1 complete revolution here for theta, would give me 1 times my circumference. Okay. So if I have a 2 pi here, times this circumference. Obviously, there's some cancellation occurring there, right? Well, what if this is 4 pi? Or what if it's 6 pi? The same cancellations occur, right? Okay. So this would be 3, and I have 3 times my circumference. Well, what we do is we say, well, those cancellations are always going to occur because you have this 2 pi and this 2 pi, one in the denominator, one in the numerator. So your distance, which we were calling S, is always equal to theta r, because that 2 pi cancellation always occurs. So if you're in radians, that cancellation is always going to happen, and you always have theta r as being that distance, okay? Or basically essentially telling you how many multiple times you're going around your circumference, okay? So what is our theta? Well, remember, theta is found by saying, it's how many times I'm going around my circle, right? Times that one 360 degrees, but right as radians, it's 2 pi. Okay, so one revolution around would be 2 pi radians. 2 revolutions around would be 4 pi. 3 would be 6 pi. 4 would be 8 pi, right? How many times am I going around? Yeah, 10,000. Okay, now this 2 pi is radians, and this 10,000 is revolutions, so revolutions is not really a unit here. If I multiply this out, I get 20,000 pi radians, right? That's the angle. If we were to let this thing, if we were to let this angle here, this theta that we've been talking about, if we let this thing go around 10,000 times, that angle that has been traced out is going to be 20,000 pi radians. Is that all right? Okay. So now, all we've got to do is plug this information in. We've got 20,000 pi radians. I like to put my units in there. Times then r, which what is r in this case? 18 inches. Okay, r is your radius, right? And they're saying my diameter is 36, so I got to put 18 in there. And I multiply that out. So when I multiply that out, I'm going to get 18 times 2 is 36, right? So I should get that number. And if I write my units like I have them here, I have radian inches. And now think about what we're talking about here, distance. And we just got a unit of radian inches. Have I ever put a tape measure against something, or a ruler against something, or got in my car and traveled a distance, or got on Google Maps and it told me, you're going to travel this many radian miles or this many radian inches? No. Radians is a dimensionless thing, right? We've talked about that. So that unit, though it's important for clarification, isn't in there. We don't put it in there to describe distance. Okay, so we have 30, and I forgot my pi here, so I apologize for that. But it's 36 or 360,000 pi inches. Is that all right? Now you type that into WebSign, you write that on a test, quiz, you are wrong. Why? It says in miles. So that is the distance. That is equivalent to the distance that we would travel, but it's not in the right unit. Okay. And if I ask you guys, how big is that? Kind of visualize how far that is. You probably have no idea, right? It's pretty large, but if we put it in miles, because very large amounts of inches are better understood in miles, you maybe have a better visual of how far this is. So let's take this number, 360,000 pi inches, and I want to convert that into miles. Okay? So if I want to convert that into miles, inches are right now in the numerator, right? What do I need down here? Yeah, it makes sense to right away try to get those units that are in the numerator to cancel out. So put inches there, okay? Now, thinking about what you want to get to, you always got to have in the back of your mind where you want to try to take these units. We're trying to get to miles, right? So I always ask myself, if I'm going to use inches right now in this first rate, or conversion factor, do I know a common value that takes inches into miles? Do I know how many inches are in 1 mile? And the answer to that is probably no, right? Okay. It's kind of like yesterday we talked about, do we know how many seconds are there in an hour? Maybe a lot of people don't know that, but you know how many seconds are in a minute, right? So it's a similar thing here. You don't know maybe how many inches are in a mile. It's probably not common knowledge to everybody. Some people might, okay? But do you know how many inches are in a foot? Right? And yeah, 12 inches for every 1 foot, right? So then, if I cancel these units out, my final answer would be in feet. Well, I don't want feet, I want miles. So I'm going to put another rate, another conversion factor here. I'll put feet down there because I want feet to go away. Now, if feet are my units, do you have a direct link between feet and the unit you want to get to of miles? Yes. Okay. I always write my units out first because we said this yesterday. If our units are wrong, our answer is wrong, right? If our units are wrong, our number doesn't matter. So I always make sure that those are correct. And then I go back and I put the factors in. 1 foot for every 12 inches, right? 1 mile for every how many feet? 5,280. Okay? So if you took, here's the thing, 12 times 5,280, there's 63,360 inches in every mile, right? Most people are not going to memorize that. Most people don't know that's common knowledge. So it's just more convenient to do it this way. So when I type this into my calculator, the only thing you got to pay attention to with this stuff, guys, if you're going to directly grab your calculator, which is absolutely nothing wrong with that, my numerator is just going to be that number right there, right? So when I type in that number, make sure I put my pi in there. That's one place where people make mistakes. But now if I divide that by 12, and then 12 is getting multiplied by 5280, right? If I do this, do I end up with the right answer? No. Okay, the order of operations, the way I've set this up, order of operations says do this division right here first, right? So it's going to take this number, this 3,600 number, 3,600,000. I keep messing up, 360,000. Take that number, divided by 12. It's going to evaluate that and then multiply by 5280. Okay? So that way of typing into my calculator has actually put this 5280 in the numerator. Does that make sense? And we don't want that. We want it to stay in the denominator. So what do I need to do? Yeah. Make sure if you've got a product in the numerator or a product in the denominator that they get isolated in their own set of parentheses. Now hit enter, and 17.8 miles is our answer. Is that a little bit easier for you to visualize than 360,000 pi inches? Yeah, okay. It's just more of a familiar unit for us as we deal with things on a regular basis. All right, so let's think about this. Let's say that it took me, I don't know, 38 minutes to do that. 38 minutes to travel at 17.84. Would you now be able to divide that and get a linear velocity? Yeah. Okay. So you'd have time, and we could go through and deal with that. Okay. So that's the relationship between linear velocity and distance or arc length. All right, so here's the next question. It says object A is traveling along a circle of radius 3, and object B is traveling along a circle of radius 6. It says these objects have the same angular speed. It says do the objects have the same linear speed? Okay, they have the same angular speed. Do they have the same linear speed? We'll answer that yes or no, and if it's no, we're going to talk about which one is greater. Okay, so here's the idea, guys, and I'll show you a visual, a second visual here in a moment. But the idea is if I take this point right there, that pink point, and let's put another point on here. Let's put that one, and I don't know, hopefully that stays stuck. There we go, good. All right, so we've got these 2 points that are on this radius, right? Okay, so maybe this is a string, and I've tied a rock here, and I've tied a rock here, and I'm going to start rotating this or spinning this string around my head, and I want to talk about the speeds, the linear velocity of those 2 rocks. They have the same angular velocity, right? Does that make sense? Okay, they're both on the same radius. The angle is changing the same for both those. Anybody want to garner or take a guess at which is the one that's going fastest? Think about this. Take this point here and move it there. Which one's going faster now? Is this point moving at all? No. So it's static, right? So this one will be moving faster, right? So if I move that point out a little bit, it's still closer to this, right? So it's still moving. Is it moving slower? Does it kind of look like it's moving slower compared to that pink dot out there? Okay. And so we're going to try to go through the work here to kind of convince you of that, that orange one, that orange point is actually moving slower. Have you ever been on a merry-go-round? Okay, you know what I mean by merry-go-round? Okay. When I was in elementary, we used to get kicked off this thing all the time because we would take, we make games like riding bulls for like 3rd or 4th graders. Okay, so we used to get a bunch of people and we start spinning this thing. Right, we put one person on it and see how long they can stay on it. Okay, but you find out that the further you stand on the merry-go-round or hold on to it from the center of the merry-go-round, the faster you move. Right, the harder it is to stay on. Okay. But if you get closer to the middle, kind of like that orange dot is, or if you're standing right on top of the middle of the merry-go-round, the pivot point, it's really easy to stay on it, right? And it's because your speed is so much slower towards the center of the circle than it is towards the outer edge of the circle. You guys been to the fair and ever ride a Gravitron? Yeah. All right, so if there would be stadium seating in the Gravitron, so you've got different rows of seating, right? The people that are closer to the center are not going to feel the same effects because they're not moving the same speed that you would be feeling in the outer edge of it, like you do when you ride the Gravitron, right? Now, there's a lot of other forces taking place there, centripetal force and that kind of stuff, but the speed in which you're moving is also, part or a component of that ride. Does that make sense? Okay. So let's go through the work here to see why it makes sense that object that is furthest away from the center is moving the fastest. Okay. What we know is that, and we've got a lot of formulas here. I think the best thing here is, because we're talking about them having the same angular speed, and the question is, what is their linear speed? Okay. We could do, I think, one of 2 things. I'm going to look at object A, and I could determine, I could say, okay, what is its linear velocity by using, r theta divided by t, right? We could do that, okay? And then do the same thing for object B. In this case, r here would be 3, right, for object A. My theta, they don't tell me theta. They don't tell me how many times I revolve, right? But they do tell me that between object A and object B, that theta, or that angular speed, is going to be the same, right? So as long as when I'm looking at object A, maybe I travel 1 revolution, then in object B, I use that constant 1 revolution. If in object A, I want to use 2 revolutions, and in object B, I'll use 2 revolutions. That kind of make sense? And then in regards to time, I would try to keep time constant. You could use that. You could use that formula. Okay? But I think this is maybe a better thing to use. Let's use velocity, linear velocity. Is that not equal to omega times r? Where omega is your angular speed or your angular velocity, And r is your radius, right? So if I'm dealing with this for object A, it says object A is traveling along a circle of radius 3. And we don't know the angular speed, so I'm just going to call it omega. I'm going to keep that as that variable. So right now, object A is traveling at 3 omega. Well, if I go object B, and I go V is equal to omega R, what is R for object B? 6. So I get 6 omega, right? And now here's the thing, is that they say the objects have the same angular speed. They have the same omega, don't they? So that omega is something that they basically cancel each other out. So if omega was 1, okay, we'd have a linear speed of 3 and a linear speed of 6, right? If omega was 2 pi, we'd have a linear speed of 6 pi and a linear speed of 12 pi, right? Regardless of whatever omega is, do you see that the linear velocity of object B is twice as big as the linear velocity of object A? Okay. So object B was further away from the center of the circle, so that has the greater linear speed. Now, the argument is, well, how do I know that this is a general fact? That if I've got these two objects, I've got this blue object here, and I've got this black object there, that the one furthest away is always going to be the fastest one. Well, think about it this way. Let's say that this radius is just A, and let's say that this radius is just B, but let's say that A is going to be less than B. Well, when I put A in here, and then I put B in here, right? Does that kind of make sense to everybody? Okay. Again, these things are going to cancel out. The omegas are going to cancel out. It's a common factor for both. So then the linear velocity of object A is predicated off of lowercase a, and the linear velocity of object B is predicated off of lowercase b, and we know lowercase a is less than lowercase b, right? So object A's linear velocity is always going to be less than object B's linear velocity if object A is closer to the center of the circle. Okay? So that's a general fact. That's a statement that I might ask of the exam at the end of the year might ask. It says, here is this statement. Okay, which object, the one closest or the one furthest away from the center of the circle, is always moving fastest. Okay, that's the one that's furthest away. Another question that you're going to see is something like this. Okay, and we're not going to get through all the examples that I want to talk about today, but I think these are going to be the ones that are most problematic for people. But if we kind of break the picture down, break the concepts down, and think about them, it's really not that difficult. What's going on here is that we've got two cities, Buffalo, New York, and Raleigh, North Carolina, and they're approximately on the same meridian. Okay, meridians are the lines that pass through the North and South Pole, right? So every meridian passes through the North Pole, every meridian passes through the South Pole. So every meridian is what we call a great circle, okay? Which means it's the biggest circle that you could get as a cross section out of the Earth, right? It's like the equator. Okay, when we talk about what are those latitudes, we talk about the latitude. The equator is the only one that we talk about in regards to a latitude as being a great circle. Okay, but every meridian, every one that goes from the North to the South Pole, is a great circle. So that's important here, because what we're saying here is because that goes to the North Pole and that goes to the South Pole, that black circle on the Earth there is going to have a radius that is equivalent to the radius of the Earth. Is that doable? Okay. Where if I talk about our latitudes, let's say I look at that latitude compared to that latitude, is this one going to have a different radius than this one? Yeah. But all meridians are going to have the same radius, and they're equivalent to the radius of the Earth. Okay. So we know that the radius of the Earth is about 3960. Okay. They want to know what is the distance between Buffalo and Raleigh. They want to know that little distance right there. So what I think is probably maybe easier for you to do and think about is to kind of look at this meridian from the side view, so it kind of looks like just a two-dimensional shape. So you would have maybe Buffalo right there and Raleigh right there. Does that make sense? Okay, so we're just kind of cutting this hemisphere off and looking at this hemisphere that has Raleigh and Buffalo kind of on that edge. If you were a person that's standing in Buffalo, New York, and you wanted to walk to Raleigh, I want you to understand that the curvature of the earth is going to impact the distance that you walk, right? If I walk from here to, I don't know, the intersection of Bible and Slabtown, the curvature of the earth affects the distance that I walk. But it's very, very, very negligible, right? The larger the gap between the two places that I go, the more the impact of the curvature of the earth, okay? So this is not just kind of a linear distance here when we're walking from Buffalo to Raleigh. There's curvature here that we have to talk about, okay? So how do we do this? What are they asking for? They're asking for that right there, right? Hopefully you realize that is arc length. So we got r theta, right? Does that make sense? Well, what is r? R is going to be the radius of that circle, correct? Which are those two radii right there, right? Does that make sense? So r is going to be 3960, and it's in miles. Now let's got to figure out theta. Well, theta here is that, right? Which, if we come back over here, it's that angle right there. Terrible job coloring. It's that angle right there. Okay? Well, how do I find that? This is how we find it. They tell us that Buffalo has a latitude of 42.9 degrees here. Yeah, 42.9. And then Raleigh has one of 35.8. So those are, when they say latitudes, that latitude is marked off of 35.8. Okay, and then all these, I believe, are referenced off the equator, right? Okay, so it's essentially that angle measurement from there. So how do we get the angle that is between these two? The idea is, and we don't have time right now to really get through why we subtract these. Maybe tomorrow I'll explain to you why we subtract these. But if we subtract these, that will give us that angle theta. Okay? So it gives me, if I subtract those, you get 7.1 degrees, right? Now, if you type that into your calculator, you're wrong. Because this is a degree now, right? And what does this theta have to be in? Radians. Okay? So if I'm going to grab my calculator, I would take 3960, open a parenthesis, type 7.1, and then multiply that by pi over 180, and that will convert that 7.1 into a radian, right? And then gives me 3960. If I do that, you're going to get about 491. Okay? Which, I think that it's a distance that kind of makes sense, doesn't it? When you're doing this, and especially a lot of these context problems that we deal with in this class, your answers should have a little bit of sense to them. Okay? If I got a distance of 7,000 miles, hopefully you understand that that's a little bit ridiculous because the radius of the Earth is 3960. Okay, so 7,000 would be quite a distance. You're also going to see, I know we're running short here, questions like this, where it says a ceiling fan. We'll get to tomorrow. I'll move back that 5 1 day 2 date